Hello everyone and welcome to today's lecture, which is the last part of the defects in solids, interfacial defects. We studied in the last few lectures point defects and line defects or dislocations, and then we are going to study the interfacial defects or surface defects. In other words, we studied 0D defects or zero dimension defects, which is the point defects, and we studied 1D defects, which is dislocations or line defects, and today we are going to study 2D defects or surface defects or interfacial defects, two-dimension defects. Interfacial defects or surface defects are the boundaries between two faces or two regions with different orientations, or any two different regions. We will come back to this concept in the end of the lecture to get more information about it. But first, we need to know what is the classification of this defects, interfacial defects. In general, this kind of defects are classified into external surfaces, any surface, grain boundaries, and twin boundaries. These three kind of interfacial defects are the most important or the most common interfacial defects in solids. First and simplest surface defects or interfacial defects is the surface, external surfaces. Closer look to the surfaces, to any surface, we found that the surface consists of atoms. But the difference between these atoms, the surface atoms and the bulk atoms, the atoms inside the material, is that the surface atoms are not saturated. They are not surrounded by atoms from everywhere. For example, this atom, the atom here, has no surrounding atoms from the above side, while this atom, any atom inside the material, is surrounded by atoms from everywhere. This means that these atoms have a higher energy than the atoms in the bulk. This energy called surface energy, and this energy expressed in unit of energy per unit area. For example, joule per meter square, or any surface area. But this is the most common. Joule per meter square. Any surface tends to reduce this surface energy to minimum, and that's why the liquid droplet, takes a spherical shape when it drops, to reduce the surface energy to minimum. And this is the first kind and the simplest kind of the interfacial defects or surface defects, external surfaces. Grain boundaries is the second and the most important kind of surface defects or interfacial defects. Actually, it occurs in almost all solids, ceramics, and metallic material. We remember from our previous study that most metallic material consists of many crystals or many grains with different orientation. We remember that from our previous study. Grain boundaries are the area between the two adjacent grains with different orientations or different arrangement of atoms. For example, the alignment of the atoms in this grain is in this direction, while the alignment of the atoms in this grain in this direction. The misalignment between the atoms in this grain and the atoms in this grain is called the grain boundary, or forms the grain boundary here and the grain boundary here. If this misalignment is small in a few degrees, for example, the misalignment between this grain and this grain is small in terms of a few degrees, it's called low angle grain boundaries. But if it is high, like the misalignment between this grain, which is that direction, and this grain, that direction, this misalignment degree is high, the grain boundary is called high angle grain boundaries. And obviously, the energy of high angle grain boundaries is higher than the energy of low angle grain boundaries. The atoms in the grain boundaries are not well bonded as they are inside the grains, which means that the atoms in the grain boundaries have higher energy than the atoms inside the grains. And this defined as the grain boundary energy. The grain boundary energy, which is the grain boundary area energy due to having these kind of defects, or the less bonded atoms in the grain boundaries area. This energy increases with the angle of misalignment, being higher for the high misalignment angle and lower for lower misalignment angle. Furthermore, all the impurity atoms tend to segregate or accumulate in the grain boundary for the same reason. Because the grain boundary area has higher energy, it attracts all the impurity atoms to accumulate here, to accumulate in these areas. Now, if we compare the area of the grain boundaries, not the area of the grains, the area of the grain boundaries for two materials, for the same material with two different grain sizes. This with the large grain size and this with the small grain size. The grain boundary area for the material with large grain size is smaller than the grain boundary area for the material with the smaller grain size. This means that the total energy, the total grain boundary energy for the material with large grains is lower than the grain boundary energy for a material with smaller grains. Again, the grain boundary energy for the material with coarse grains or large grains is lower than the grain boundary energy for the material, for any material with smaller grains or fine grains, because of the grain boundary area for the for a material with smaller grains is higher than the grain boundary area, surface area of the grain boundary for the material with large grains. The grain boundary, or having the grain boundaries, does not affect does not have that effect on the density on the material. A solid material with single crystal has the same density as that with polycrystalline. Polycrystalline material, polycrystalline structure for the same material has the same density as a single crystal structure material for the same material. And grain boundaries does not have impact on the strength as well. The strength for solid for polycrystalline material is still high. And in some time, as we will see in the coming slides, that these areas work as strengthening for the material. As mentioned in the last slide, that the energy of the grain boundary is higher than the energy of the grains. The energy of the grain, because the energy of the grain boundary is higher than the energy of the grains, because the atoms in the grain boundary is not well bonded as the atoms inside the grains. And having said that, means that the chemical activity of the grain boundary area is higher than the chemical activity of the grains, because the chemical activity of metallic solids increases with the energy stored in the material. And because the energy stored in the grain boundary is higher than the energy stored in the grain, the chemical activity of the grain boundaries is higher than the chemical activity of the grains. Again, the chemical activity of the grain boundary is higher than the chemical activity of the grains, because the energy stored in the grain boundary is higher than the energy of the grains. Another type of interfacial defects is twin boundaries. Twin boundaries occurs when some atoms or group of atoms shift from its initial position under applied stress, under external stress. For example, this group of atoms with initial position or initial arrangement for a material, the material exposed to external stresses, leading to get some of these atoms, a group of atoms, out of the position, out of their initial position. Now, under the applied stress, under external stress, this group of atoms shift from its initial position to go to a new position. The boundary between the boundary between the atoms in the new position and the atoms in the initial position is called the twin boundary. As we can see here, this is the atoms with initial position, and these are the atoms with the new position after shifting. The boundary between them is called twin boundaries, and this area here called the twin. A twin always occurs at high temperature, but it also can occur at room temperature. I will come back to this sentence in the end of the lecture to explain it with more details. At this point, we went through the most important defects in solids, in metallic solids, including dislocations, point defects, grain boundaries, and others. And now we need to understand and we need to know what is the importance of these defects. Are they beneficial or detrimental on the mechanical properties of metallic material? We are also aware that the strength of the material or the plastic deformation of the metals and alloys mainly depends on the dislocation motion. Thus, anything impedes or prevents dislocation motion makes the metal stronger. Thus, based on this concept, we can control the mechanical properties of the metals and alloys by playing with the defects, with these defects, the amount of them, the shape of them for metals and alloys. And in the coming slides, we will get more ideas about these effects. We know that the plastic deformation or the strength of the material, of the metallic material, mainly depends on the dislocation motion. However, the dislocation number in the metallic material has a major effect on the strength of the material. The dislocation numbers in the metallic material has a major effect on the strength of the material. I prefer to explain this on the figure in spite of reading the text. Let's take this material with the dislocation A here. This is dislocation A, extra half plane A, and dislocation B here, extra half plane here. Each of which causes a compression of the atoms around it. For example, dislocation A causes compression of the atoms above it and stretching of the atoms below it. Dislocation B causes the same effects, compressing of the atoms around it here and stretching the material around it here. Let's propose that this material is exposed to external stress, leading to dislocation A to move to this in this direction. Now dislocation A moves in this direction freely until reaches the dislocation B. And because the structure of the material in dislocation B is not the perfect structure, dislocation A needs higher stress to pass through the area here. And if dislocation B was not here, dislocation A would need less stress to pass through this area. Again, because the structure of the material here is not the perfect structure, is different from the perfect, deviated from the perfect structure. When another dislocation, like dislocation A, moves toward this area, the area with another dislocation, it needs higher stress to pass through this area. Which means the metals with higher dislocations, higher number of dislocations, needs higher stresses to deform. Or in other words, the metals with higher number of dislocations is stronger than the metals with lower number of dislocations. The metals with higher number of dislocations is stronger than the metals with lower number of dislocations because the interaction among dislocation movement, the interaction among dislocation motion. We can increase the number of dislocation in a metallic material by deform the material. For example, doing forging or rolling or any deformation process on the metals. And what is called strain hardening. Thus, strain hardening is increasing the strength of the material by increasing the number of dislocation inside the material, causing interaction or disruption of the dislocation movement across the material due to the interaction among the dislocations. We also can make the material softer by decreasing the number of dislocation. Decreasing the number of dislocations causes softening the material. We can do that by raising the temperature of the material, of the metallic material, to relatively high material, but below melting temperature, and holding the temperature there for some time. And what is called annealing. Those we can control, we can make the material softer by decreasing the number of dislocations, or we can make it harder or stronger by increasing the number of dislocations and what is called strain hardening. In the same way, we can interfere the dislocation movement by another mechanism. For example, here we have a point defects in this structure, and we have the same dislocation A. When dislocation under the applied, when this dislocation A under external stresses moves to the left, it will counter the point defects here, and it needs higher stresses to go through the area here, or to pass through the area here, because the point defects introduces imperfection in the solid. And slipping through this imperfection is more difficult than slipping into the perfect structure. Those we can control the mechanical properties by intentionally introduce point defects. For example, introducing interstitial point defects or substitutional point defects. Both of them introduces imperfection in the crystal structure, and causes increasing the stress needed for the dislocation to move, or for the dislocation to slip through the structure. This is called solid solution strengthening. And this is exactly what we are doing when we cast the ion Fe with carbon to introduce point defects. And these point defects cause interruption for the dislocation movement, leading to form steel, which has much higher strength than the ion itself. Grain boundaries do the same job in interfering the dislocation motion. For example, if we propose that under applied stress, under external stress, dislocation B would move to the right. It will be able to move until it reaches the grain boundary. The grain boundary, as we explained earlier, is the area that the atoms are not properly bonded. The dislocation will stop here and block here on the grain boundary. The dislocation cannot move through the grain boundary. Those grain boundaries do the same job of strengthening the material, and this leads to increase the strength of the material. Thus, we can increase the strength of the material, of the metallic material, by increasing the grain boundary, or in other words, by decreasing the grain size of the metallic material. Increasing the grain boundaries or decreasing the grain size. In other words, decreasing the grain size, because when we decrease the grain size, we increase the grain boundary area, and we increase the interfering of the dislocation movement by the grain boundaries. We also can make the material softer by increasing the grain size. And we can decrease the grain size and increase the grain size by what is called the heat treatment. Based on the grain boundary strengthening, there is a very nice relationship between the yield strength and the average diameter of the grains, or the grain size, which is called the whole pitch equation. In whole pitch equation, the yield strength is inversely proportional to the grain size. In other words, with decreasing the grain size, sigma y increases. With increasing the grain size, sigma y decreases. Sigma naught and k are constants for this equation, and sigma y is called the frictional stress required to move the dislocation. The frictional stress required to move the dislocation. It is constant. It's measured for any single material. K is the whole pitch equation slope. HB whole pitch equation slope. Whole pitch equation is valid for most material with different grain size. However, it's not valid for material with unusually large or ultra fine grains. It is invalid for material with very large grains, or material with very fine grains, or even nanograins. Let's take a mathematical example explains how do we use whole pitch equation, how do we make it useful. The example says the yield strength of mild steel with an average grain size 50 micrometer is 138 megapascal. And the yield strength or the yield stress of the same steel with a grain size of 7 micrometer is 276 megapascal. What will be the average grain size of the same steel with the yield stress of 207 megapascal, assuming whole pitch equation is valid? Now, first thing to note from this equation, from this example, is that with decreasing the grain size from 50 to 7 micrometer, the yield strength, the yield stress increases from 138 to 276. Now, because the example says that or gives us two different yield stress and grain size, average grain size, we can use them to calculate sigma naught and k by using whole pitch equation to calculate the constants of the whole pitch equation. But before doing so, we need to convert the grain size from micrometer to millimeter because the stress in megapascal. Thus, the grain size should be or has to be in millimeter. And doing so, we can use the whole equation for the two cases to get sigma naught and k by solving these two equations instantaneously. And when we got these, we can apply them the whole pitch equation again to get the D needed for the 207 megapascal. Putting 207 megapascal here and calculate D. Thus, for 207 megapascal sigma y, we need 14.8 micrometer grain size.